Assalamualaikum warahmatullahi wabarakatuh, and my name is Sophia Radini Majid. Okay, so for today, I will be presenting our analysis of organ donation pledge in Malaysia, focusing on the period from 11 April 2024 to 11 May 2025. Okay, first, organ donation is a generous and life-saving act. In Malaysia, we have seen a rising number of registered donors, especially with the help of a digital platform like MAT523, which make pledging more accessible and convenient. Okay, our study used the publicly available data sets titled Organ Donation Pledged by State from the Ministry of Health of Data Culture. We focus on daily pledging activity during a month period, and it is a part of a budget 12-month calendar year analysis. Okay, to understand the trend in pledging behavior, we apply curve fitting techniques using three mathematical models. First, we use linear, and second quadratic, and third is cubic. Okay, this allow us to see which model best describe the pattern of pledge during our study period. To ensure accuracy, we use both manual calculations and maple software to compare the models and select the one that best fit the data. Okay, our goal was to identify not only trends but also the most reliable model to predict future organ donation pledging behavior in Malaysia.
Now for the methodology, we have three methods used, which is linear model, quadratic model, and cubic model. I will be presenting topic 2.1, linear model. We begin with the general linear equation y equal to a plus bx. This represents a straight line relationship between the dependent variable y and the independent variable x. To solve for the best fit line, we can represent our data in matrix form, as you can see on the slide. To find the best fit line, we use the least square solution, which minimizes the total error between the observed data and predicted line. The formula used is m transpose m times v equal to m transpose y. Substituting the matrices and solving for v, we get the constants of a and b. Now, let's look at how accurate our linear model is. We calculate the error vector e by subtracting the predicted values from observed values, e equal to y minus mv. Here, mv is the vector of predicted values using our linear model and y is the actual data. This gives us the differences or residuals for each point. To summarize the overall error, we compute the magnitude of the error vector. In this case, the magnitude of the error is 134.1784. This number represents the overall discrepancy between the model and the real data. A smaller value means a better fit. In the final slide, we visualize our result. On the left graph, we have the best fit line in blue and the actual observed data in red. While on the right graph, we have the error vector plotted against the x values.
Now we move on to the next quadratic model of the data. For this model, the general equation is y equal to a plus bx plus cx squared. After substitute all independent and dependent variables into the equation, we got mv equals to y, which represents the matrix of the system. Then, we can derive the normal system by calculating that m transpose multiplied by y, and we get the least square solution by making v as subject. Then we are able to find the equation of the best fit quadratic curve with the solution. After that, we need to calculate the list of error vector by using the formula e equal to y minus m. When we get the error magnitude of the model as square root of 145,944,435 divided by 91 using x formula. From this equation, we again observe data and the graph of the error vector against the x value.
I will be presenting about the cubic model, which is a form of polynomial relation is used to fit a cubic curve to a set of data points. We start with the general form of a cubic equation, y equal to the a plus bx plus cx squared plus dx cubed. In this model, we want to determine the best value of the constant a, b, c, and d that make the curve best fit the given data. On the left side of the slide, you can see the metric representation of the system. Each row represents an equation based on one data point, with x squared, and x cubed value filled in accordingly. The metric on the right hand side represents the corresponding y value. This system is then used to form what we call the normal equation. These are derived using metric multiplication to minimize the error in the least square method. The normal equation is MTMV equal to MTY, where M is the matrix of X value, Y is the output vector, and V contain the coefficient A, B, C, and D. Now, moving to the right side of the slide, you can see the least square solution. The equation is solved using matrix operation and inverse matrix. The final solution gives us the value of A, B, C, and D. At the bottom, we get our final result. The best fit cubic curve is Y equal to 10,820 divided by 33 minus 1,489,291 divided by 18,088 plus 75,930 divided by 6,006x squared minus 799 divided by 1,287x cubed. Here we see the error vector E, which is defined as E equal to Y minus MV. This equation represents the difference between the actual output Y and the model output MV, where M is the matrix applied to the V. On the left side of the image, two columns display the original output matrix Y and the compute model output MV. The value corresponds to the specific data point indexed along the vertical axis. Each row comparison shows how closely the model approximates the actual data. Significant difference indicate where the model underperformed. At the bottom of the image, the norm of the error vector modulus E is calculated, yielding a value of 35,314 divided by 429. Next, on the left side of the slide, we can see the best fit curve plot against the observed data. This curve represents a cubic function which is capable of capturing more complex relationships compared to the linear or quadratic model. As you can observe, the shape of the curve bends in the multiple directions, which indicate the flexibility of a cubic model in adapting to data with non-linear patterns. Moving to the graph on the right, this is the error vector plot against the X value. The error vector shows the difference between the observed value and the value predicted by the model. Ideally, we aim for this error to be as small and evenly distributed as possible. However, in this case, we can see some noticeable spike, which suggests that why the model fit the overall trend. There are specific data points with high deviation. It is useful for diagnosing how well the model generalizes. In conclusion, the cubic model offers a more flexible fit for non-linear data as shown by the curve on the left. However, the error graph reminds us that model accuracy should always be validated through error analysis.
Okay, for the analysis and conclusion, comparison of the curve models for the model type MAT2. Okay, first we have a linear model, we have 134.1784. Okay, for the quadratic model, we got 132.755. Okay, for the third model cubic, we got 82.3170. Okay, for the conclusion, among this model test, linear, quadratic, and cubic, the cubic models provide the best approximation because it has the lowest error magnitude and indicating a better fit for the organization data.